Okay, so looking here, talking about the rate constant. There are factors that affect the rate constant, and we'll be using the rate constant K throughout the integrated rate law formulas as well. And we'll be addressing these particular ways of affecting K also at the end of the notes when we talk about the Arrhenius equation. But the rate constant, K, obviously, is just a constant value depending upon which reaction you have here. Things affect the rate constant, though, because we have our methods of speeding up chemical reactions, like in that how to get a date for the dance video. Temperature, particle size, surface area, catalysts, all of those factors are actually put into the K value, mathematically put into the K value through the Arrhenius equation. The only one that is not is concentration. The big exception here is concentration. Concentration is already a part of the rate law. It's in the differential rate law because rate equals K times the concentration of each reactant to their order of their reactant. And you'll also notice in the integrated rate law formulas, the concentrations are built in as well. So concentration, separate entity. We know that when we do change the concentration of the zero order, nothing changes the rate. We know that if we change the concentration for first order, that same factor will also affect the rate. We know that when we change the concentration for second order, it is square of the change, and that would be like squaring the rate, okay? So thinking about these things, not to get it confused with equilibrium, which is the capital K. That one is only affected by temperature. Again, it doesn't have units, as we were just talking about K units. It doesn't have units like the rate constant K does. So keep that in mind, keep that separate. Now let's talk about the differential graphs before we move on to the integrated rate law graphs. Differential, remember, is always about a function of looking and comparing at the concentration versus the rate. So the ones we were just calculating in part one, those are differential rate laws. The concentration versus rate for the zeroth order, you notice it's just a straight line because the rate does not change. It doesn't matter what you do to the concentration, it stays the same. So it's just a horizontal line on the graph. And that means rate is just equal to the rate constant because the concentration does not affect the overall rate. So this is the no change. Remember, this one falls under the no change idea. First order, concentration versus rate. Linear relationship. Here's our first order. It is, the rate equals the constant times concentration. Okay? And as you know, this is the same change. We have the no change, this is the same change. So whatever we do to the concentration, that is the factor that will affect the rate. And that's why it's a nice linear relationship. Last one, concentration versus rate for second order. So you can see it's more of an exponential type curve, because this is the square of the change. So it's going to be more of an ever increasing, more like an exponential curve there. The reason why I point these graphs out now is because notice the rate is on the Y. They can find themselves into multiple choice questions very easily. And you're expected to know, if it's talking concentration versus rate, what those trends should look like. That's talking about it in terms of the differential rate law. And then looking at it now, we're going to start looking at it in terms of integrated. Integrated takes into account different factors. So differential rate versus, or concentration versus rate, but we know integrated, the concentrations depend on the time. So we're looking now at relationships between our data points where one of the data points will be the concentration, the other data points are going to be the time of where the reaction occurs. So integrated, now we're looking at data sets versus time. And we're going to be doing a graphical analysis just like we just did with differential. And that graphical analysis is going to provide us lots of information about the order of the reactant. And integrated rate laws really focus on the order of just individual reactants, not putting them all together in one big rate law equation. What we're looking for, the relationship of concentration versus time, but then we do our graphical analysis of that concentration versus time data, and we're going to be looking for the linear relationship or the straight line. We're going to have three choices. We're going to have the zero order, so that's going to be concentration versus time. If this one gives you the linear relationship, it's going to be zero order. Now, for first order, it's going to be the natural log of the concentration versus time. If the natural log of the concentrations versus time gives you the straight line, then it's going to be the reactant, order of reactants going to be first order. The last one is looking at the inverse. So like 1 over the concentration versus time. In that particular case, the inverse of the concentration versus time, if that gives you the straight line, it's going to be second order reactant. So we look at the graphical analysis of these three different ways of calculating our data. Whichever one comes out with that linear relationship is going to tell us that the order of the reactant is a certain value, whether it's zero, first, or second. Let's talk about first order. What you notice in the formula, I just told you the natural log of the concentration versus time, the linear relationship is first order. You see natural logs in the formula. And this is on your formula sheet, however, they write it like this on your formula sheet, which is just moving this over to the other side. So you'll notice on the formula sheet it's written as such. I like writing it the other way. You'll see it both ways if you Google or look in various textbooks. I like the first one better because it shows the linear relationship, like so. Now, concentration of A at time t, of course, that's going to be the second concentration or the final concentration that you're looking at, whereas the concentration right here with the little zero, that means A naught, we're talking initial concentration there. K, of course, is the lowercase k is still the rate constant, so that doesn't change. Now time t is factored into the formula, so we'll be looking at the time t in there as well. Different ways to look at it here. Once again, this also draws in the idea that you can use the natural, log function, concentration of time t over concentration of A naught, like so. Because the subtraction on the natural log function allows you to go straight to that division. But you also could just do the subtraction in your calculator and it does it for you too, okay? Just saying. So that linear relationship, good. Here's the data table, and they don't normally give it to you in ln concentration. They normally give it to you in concentration, and you're supposed to calculate it. Sometimes you might see it like this, but the key is first order, natural log of the concentration versus time. You get the nice linear relationship, linear graph. We know it's going to be first order, okay? Now, one other thing to point out about the graph. Negative k equals the slope. So the rate constant is Obviously, the way the line's going, it's in a negative direction, so they have the negative in front of the K because the rate constant K can't be a negative value. But as you see, since it's sloping downward, it is a negative trend. So negative K equals the slope. So if you're given the graph, you can always, do the slope of the line and figure out your rate constant if necessary. That's another added fun little tidbit here. But yes, you should start focusing in on the fact that these are natural logs of concentration versus time, giving you a linear relationship from that formula. That is going to be a first order reactant. All right, let's look at first order half-life. This is the only one that they actually expect you to be able to calculate using the formula. The other half-life ones, there are formulas for them, but you don't have to do the calculations. You just have to kind of understand the trend. First order half-life, time required for a reactant to reach half of its original concentration. It's very similar to the radioactive decay, except for radioactive decay, it was for half of the radioactive isotopes to change into the stable daughter isotopes. So half of it changes over, half its original concentration. That's what we're going for here in terms of kinetics and half-life for reactions. Now, the formula is T half-life, which is the T half here. T half-life is 0.693 over the rate constant. That means that it does not depend on concentration. Concentration does not affect the half-life. The half-life is going to be a selected time for each value. It's constant. So the half-life, if you notice, the half-life is staying at 10 minutes for each time it takes to make the concentration, divide in half. Then you know it's first order. You can tell first order, if the half-life is constant, you know it's first order. Radioactive decay follows first order. Like carbon-14's half-life is like 5,700 years, something like that. So every 5,700 years, half of the sample will change over into its daughter isotopes. So radioactive decay follows first order kinetics here, and it has a constant half-life. Now, we're not going to have time to watch it today, but there's a really good Khan Academy video that shows how this formula is derived off of the graph. I do suggest you watch it. We might not be able to do that on Friday or next class. So we'll probably try to watch it in the next plus period. But it's really good, especially for people who need the visual aid with the math and where these equations come from and how they end up, the variables equal whatever. I would recommend definitely watching that. So we'll take a look at it next Thursday. The link is right here. Yes. So if you want to watch it before plus, you can. And where that half-life integrated, or that half-life formula comes from in terms of the integrated formula for first order. It's actually done very well. They use lots of really pretty colors in the graphing segment, just so you know. All right, let's look at example 1. And let's talk about, this is a first order kinetics problem because it tells us it's a first order reaction. 35% complete at the end of 55 minutes. What is the value of K? Well, 35%, 55 minutes, those are two key data points that we need. We know this is first order, so we can go ahead, write down our first order. Okay, definitely going to use that formula for first order. However, they didn't give us concentrations. It's very frustrating when they don't do that. They gave us percentages here. So what do you do when they give you percentages and not the concentration?
Where's the decimal place?
yes, definitely like that idea, saying that 0.35 molar is complete here. So this would be like your products. You basically make up your own numbers that fit the percentage. So what does that mean about how much is left here at this point if 35% changed over into products? 0.35 molar? 0.65 must be reactants, right? That is still reactants at this point. So what does that mean in terms of what we initially started with? What would we declare our initial concentration to be? 1 molar, thank you. That's exactly right. Like 100%, right? 1 molar, there you go. All right, so now we know values, right? We know the initial concentration. This is going to be your concentration at time t that's left because that's how much of the reactant is left, right? So this is time t. And we also know 55 minutes. So guess what? T equals 55 minutes. Can we plug and chug now? Can we put it into the formula if we figured out all of our values? Yes, you can. ln of 0.65 equals negative k times 55 plus ln of 1.
Is time always going to be in minutes?
No, time can be in seconds. Good question. Time can be in hours. Time can be whatever they designate it, but you just use that particular unit.
Okay.
So time doesn't always have to be in minutes. It is minutes this time. And yes, when we do our K units, we're going to have to use minutes for the time.
Okay.
So you do the calculations. You could set it up like this, right? Where you do it this way. And you're using the log properties. Like so. But what does K end up being? What do we get for K? When we calculate here. You use your natural log button, it doesn't matter if you subtract or actually do the natural log of 0.65 divided by 1. Either way, you'll get the same answer. So what do we got going on here?
Where is the natural log button?
The natural log button,
Oh, I found it.
it's on my left side, yeah, under log. So if you're looking for natural log on the TI-84s, 83s, they're usually down the left side. If not, look for the LN button. You should have one. So what is our value for K here?
7.8 times 10 to the negative 3.
7.8 times 10 to the minus 3 is correct. We're using 2 significant digits because that's all they gave us in our measured values in the problem. Now we do have to do the units. Don't forget, we have to do our lovely units. Here's the K value. Now, instead of trying to do the derivation from the problem here, what you should just do is use the formula that I gave you. 1 over m to the n minus 1 times the time. Well, what type of reaction is this? It's a first order. So this is going to be 1 over m to the 1 minus 1 times the minutes. So really, m to the 0 power is gone. So this ends up being 1 over minutes for our rate constant. And you should notice that for a first order reactant, it's always just going to be 1 over the time because the molars were going to cancel. Now you could write it like this as well. If you prefer the non-fraction way, the minute to the minus 1, that will also work for that particular problem in terms of the rate constant units, which you have to have. Once again, rate constant units are important. Very, very important. All right, next. Good to go? Makes sense? Plug and chug, use the formula on the formula sheet. Don't have to memorize.
Plug and chug. Here's the formula. Plug and chug. Here's the formula.
All right, what is the half-life of a first order reaction that starts with 1 molar solution and K equals 1 times 3 times 10 to the minus 2, 1.3 times 10 to the minus 2 per second? What do we do here for this particular problem? What do I need to look at? What do I need to use?
Could you use the T1/2 time equation?
Could use the half-life equation. Definitely could do that. We have the K, which is all we need really for the first order half-life. It tells us it's first order anyways. So T half-life equals 0.693 over K. We write out our formula, plug in the value, and what is our half-life? How many seconds? How many seconds for our half-life? 53 seconds. Very good. So 53 seconds equals T half-life here. Not too hard. Pretty easy stuff. Tells us it's first order. We go to the first order formula. This one's on your formula sheet, so you don't have to memorize it, along with the first order, zero order, and second order general equations. There we go, half-life, 53 seconds. All right, let's talk second order. Integrated rate law, second order. I told you before it's the inverse of the concentration versus time. When that's the linear relationship, the order of the reactant happens to be second order. Now, this is at time t, this is at time t. Same idea here. It's the same y equals mx plus b deal. The way this is written now on the formula sheet, like I said, they'll move this particular one over to the other side, and they'll have it subtracting. But it's the same formula. And like I said, either they tell you in the problem that it's second order, or they give you the 3 graphs, and the one with the linear relationship, that's how you pick out which order to use, which particular formula to use. So looking here and comparing these two different plots for our C4H6, which I believe is going to be, I think that's butane. But if you look at the axes, this is the natural log versus time, and this one is the inverse of the concentration versus time. The one that's the linear relationship happens to be this one. So obviously it's second order. Now, the slope is also still K. In this case, because this one goes up, has a, increasing trend. You don't have to have the negative sign in front of the K. The slope still equals K, and you can figure it out from the graph if necessary. If they don't tell you in the problem and don't say it's second order or first order, they either have to give you data where you figure out the graphs, or they have to give you the graphs to tell you as well. There's other ways too that they can hint to you, which I'm going to show you as to what type of order it's going to be. But most of the time nowadays, it's going to be a graphical analysis that leads you to which order you're dealing with. The linear relationship, yeah. All right, so You can write this down, but really we don't use this formula. It is the half-life formula for second order. What you can do also is derive it from the main formula. However, they're not going to ever have you calculate any second order half-lives. But what you should notice about second order half-life is it gets longer as the reaction progresses. The half-lives grow. As the concentration decreases, the half-life gets longer. Each successive half-life is double the preceding one. That's what you need to be able to notice. Oh, the half-lives get longer. Oh, it must be second order. If they give you half-life information.